but I am from Dell EMC. We are a founding member of GenZ, and my boss is the president of it, and I'm the technical representative. So what I want to go through is not only what GenZ is at the next level down, but some of the motivations and some topologies. So back to some of the original questions we had. Why come up with a new bus? System memory is flat and shrinking, so these are some of the architectural motivations from the CPU or platform. Memory bandwidth per core continues to decrease. Memory capacity per core is generally flat. Memory is changing on different cadence compared to the CPUs. What I mean is we have flash memories that rely on new updates in the CPU, and so we cannot get the innovations that we want on our flash memory or 3D Crosspoint or MRAM or just numerous other kinds of memories, and they have to wait for the cadence delivery from the CPU. So there's the concept where we want to break the media controller away from the CPU, take that and have a more generic interface going between the CPU and the memory. Right now you're dealing with DDR3, DDR4 kinds of interfaces. Data is growing, as anyone knows in this industry. The amount of data has to come into the memory, not just be out on the storage. So we have a continuing ballooning of memory. Some of the products that we're shipping now, we have 6 terabytes of DRAM in our product, huge amounts of memory. The industry needs an open architecture. Memory tiering, we're going to have different kinds of speeds with flash memories and persistent memories. The speeds are becoming DRAM capable, but there's still going to be some hierarchy of speeds to that. There's going to be reasons why your OSs will want to have some banks of memory that have more persistency and less speed and so forth, and more capacity. We also want ways that we can plug this seamlessly into our OSs. I put in what I call an obligatory memory pyramid. I think everyone that's ever seen memory discussions had it from the bottom. This pyramid seems to be ambiguous all over the place. Up on the top we have on package memory. All the major SoC and processor companies are talking about putting more and more memory, consuming memory channels on the die itself and putting DRAM directly on the die, which will be the fastest. Regular DRAM, we don't expect to ever probably replace all of the DRAM. Its speed is going to continue to increase. There'll be several channels of DRAM coming out. Down at the bottom, there's going to be storage. We're still going to have spinning storage. We'll probably have a lot of flash storage for at least the spinning storage for the foreseeable future, and definitely large storage into the future as well. But now we get into what we call FCM, or storage class memory. So what is that? That's basically a persistent memory, has the RAS features that the enterprise requires, and near DRAM speed. So we do see a transition over time. Right now we have memory and we have storage, but as SCM gets more and more into it, we expect that the more the problem will be consumed in the SCM memory. And so as we go across in time, this diagram kind of illustrates that. Some of the kinds of memory that we talk about are hypermemory cube. HBM refers to high bandwidth memory. And I know there's 3D stacked memory, there's MRAM, there's RRAM, the litany of different types of memories is just boggling. So I am a hardware engineer, and so why do I want to have a different kind of memory? The reason is this is a picture of a 4-way processor using our friends at Intel's processors. And I think this one has 48 DIMM slots. Basically, it has the memory bandwidth requirements are driving, the number of channels is growing. The number of DIMMs per channel is unfortunately shrinking. because of the speeds, you guys have populated servers before. You know, you put one rank in, you get one speed. You put two DIMMs in, you get another speed. You put 3 in. We're not even going to give you the option for 3 anymore, so it's 2. And then in the next generations, you will see that when you put 2 DIMMs in, your speed will definitely decrease because of the laws of physics. We haven't been able to repeal those laws yet. The power in the DIMMs are growing. I mean, just the Ohm's law of going through the DIMMs, they consume more power. The size of the CPUs are growing, if you've noticed. The geometric size of them is growing. The size of the DIMMs, unfortunately. I've talked, Jetic's talking about making their DIMMs in excess of 300 pins and probably another quarter of an inch longer. Wonderful. The size of the speed of the memory channels is growing, as we said. We talked about we'll probably only have 1 DIMM per channel, and we'll probably be in excess of 3,000 on the speed of the DIMM channel. The number of cores in each socket's growing. You've seen 4, 8, 16, and now with the stuff coming out of Intel, the PHY parts, where you have 30 cores or 80 cores or more, and you've probably seen their roadmaps. It's growing very large. Customer requirements, their memories are growing through the roof, and every customer we talk to, they always want more memory, and we just say, wow. Not to mention, the other thing that grows the real estate problem in here is we want more I/O buses, more integrated graphics, more GPUs, more FPGAs, so we just become a real room problem. So this is about the same diagram you saw from the previous slide. So what is a memory-semantic fabric? It handles all communications as operations such as load stores, puts and gets, and atomic operations typically used by the processor. And that's what the gentleman from AMD was talking about earlier. So we're not sending across block transfers, but we're actually having load stores or asking the memory appliance a question. And when I say a question, where it can do some mathematic or some logical calculation across some address range and give us an answer back in an atomic operation. Memory semantics are optimal at sub-microsecond latencies from the CPU load store to register. So that kind of gives you where we're talking about. Sub-microsecond. So we're talking about going through switches at about 30 to 40 nanoseconds. Why now? The emergence of low latency storage class memory and the demand of large capacity, rack scale resource pools and multi-node architectures make it demand. So and we'll get to some of the architectures we have in mind later, but we're talking about as memory appliances as opposed to disk appliances. GenC Attributes, let's talk a little bit about that. It's a packetized transport, scalable and powerful proportional links. The AMD gentleman talked about the width of can be from 1 to 256. We talked about speeds from 25 gigatransfers to 112 gigatransfers. Scalable and powerful proportional to the links, physical underlying memory media access. What I mean by the underlying memory media access is we've tried to split that media controller away from the CPU and put it in the memory. The split memory controller paradigm hides the microarchitecture details and the idiosyncrasies of the memory itself. So let the media controller in the media device take care of it. Let the CPU not know about it. Talk to it in a generic way. GENZ data access technology. It has high performance, low latency, memory semantics, simple reads and writes. From tens of thousands to 100 gigabytes of bandwidth, sub 100 nanoseconds, kind of what we said before. Applications where we see it, real-time analytics, enabled data-centric and hybrid computing, that doing processing in the memory. Scalable memory pools for in-memory applications, abstract media interfaces, provides end-to-end connectivity from node level to rack. So we're talking about not only inside the chassis, inside the box, across that entire rack through switching. So you might have 16, 32 processors that try to hit the same memory appliance. Implementation from simple, low cost to highly capable, robust. That sounds like a marketing line. Leveraging high value IEEE physical layer and broad, deep industry ecosystem. Simply what that says is we're using 802.3 drivers technology. So that's what that's. GenC Attributes continued, supports processor-centric and memory-centric architectures. Both, we can continue with the processor-centric architectures, just have plain old memory, or we can branch out into these process in-memory compute platforms. Market-driven packaging and fabric topologies. Single and multi-link point-to-point topologies are accepted. Switch topologies are defined in the spec. It has the GenC has the concept of components. You don't talk to the memory itself, you talk to a component, which could be a media controller, could be an FPGA, could be a GPU, could be another processor. So you have these 2,000 components you can talk to. So that's what you're addressing. Hence, any InfiniBand experts know that your cut-through addressing, how many bytes you have to read to get the address, that's the advantage of only having 2,000 things to look up. Your lookup tables become very small. You can get to the data really quick. So what do you ship across to it? You ship address and you ship data. You ship a question, you get an answer. And we also talked about cache coherency. The specification is rich with cache coherent type instructions, but it does not claim to have the answer for cache coherency. There's going to have to be some work done on top of that. Workload and environmentally driven optimal capabilities. It can be, the interfaces can be asymmetric to one another. The transmit can be so many lanes, the receive can be so many lanes if you have an asymmetric problem. It can be dynamic. We can change the number and length of width. The problem with C6 and PCIe, we've looked at PCIe for many years, and we've built products on top of PCIe switching. It's great for internal to box, but when you get to large-scale switching, it becomes a nightmare to add, subtract nodes dynamically. And the whole goal of this is we want to be able to add, subtract components throughout the system dynamically. Never take the system down. Memory persistency is going to be another area that this is very driven to. It also has a lot of hooks in it for advanced and vendor defined operations. If we look through the ISA, and basically the specifications, about 700 or 800 pages, has significant holes in it for the application of vendor defined specific operations. It has strong data integrity going across for end-to-end communications. And it is, we hope to be OS and processor independent. We talked earlier about the addressing. It has multiple ways of talking in the address space. 2 to the 44th or 202 to the 64th bits of address can be shipped across. And as I said earlier, up to 2,000 components can be addressed. It can be a point-to-point trivial net. It can be a fabric, a star fabric. It can be a torus. It can be, the topologies are arbitrary. I said earlier about breaking the processor controller deadlock that we have. The way we do that is we take the media controller, keep that on the media side. The media controller that's on the processor side initiates high-level requests, read writes, atomic, puts, gets, and enforces the ordering because this is a fabric so things can get out of order, as you guys well know. Reliability and path selection. On the media controller, its job is to abstract the media, the memory media supports and validates, supports volatile and non-volatile and mixed media, performs media-specific operations. Every one of these new memory technologies has some bizarre code paths that has to be executed to keep it refreshed or keep it coherent or to flush it or to get rid of it. You know, there's lots of media-specific types of operations that have to happen. It enables data-centric computing, accelerators, FPGAs, GPUs. It does have huge RDMA engines built into the protocol. It eliminates need for type timing budgets within the processor because we have virtualized it. And it has transparent and caching and acceleration to improve performance. Again, this is a picture showing how, if you were to take a study of this, how that memory media controller is broken apart. This has, there's two types. This is a diagram of how the switch would be between the processor and the component or the memory or whatever the component is. And there's a switch that, so the link-to-link packets go in between the processor and the switch, and there's new link-to-link packets that are established between the switch and the component. And the end-to-end packets are going all the way across. That's fairly obvious. The spec itself is broken into op classes. There's op codes and there's op classes. Op classes are the general family of instructions that are broken in. So there's point-to-point core op class. These support the topologies of just point-to-point, simpler, non-switchable protocol. The advantage of that is they're not transporting an address, and they can be very, very fast, very efficient, even faster than the advertised 30 nanoseconds. Core op class is where the bulk of the instructions are. It's implicit, does not contain the op class label, so it's implicit. There's no decode to know that you're going further than that. Packets associated with op class core may be exchanged on any interface and not enabled for peer-to-peer core op class or implicit vendor-defined op classes. Then we have the core instructions which have expanded the address space. So we go from that 44 bits up to 64 bits, which is where the core 64 instructions go. There's an op class called control. Control op classes are used to access configurations, resources located in the control space. The memory space is broken into user space and control space, so there's ways you can set up your control mechanisms for your component via this control space. As I stated earlier, there is a whole set of atomic instructions, and this is its own op class. Large data movements, I told you there was a significant amount of effort spent on specific DMA engines inside, and so these DMA engines are defined in this op class. Some of the comparisons, some of the op math instructions going across are contained in the advanced op class. They do have multicast op class so that you can send information to multiple places simultaneously, and it keeps track of that. Strong order for ordered packet communication, where order is significantly important to that specific kind of communication. And then I also said there's reserved areas for vendor-defined op classes. We talked earlier that GENZ supports a set of operations to allow cache coherency. Some of the examples of some of those instructions are invalidates, write-backs, write with target cache, read modify, read exclusive, etc. We believe cache coherency protocols are customized to a given processor ISA. It's going to be tough to have brand x86 be cache coherent with brand Power 9. It's really a lofty thing to do, but there's going to be lots of things before that can happen. We believe this area is going to be a source of innovation and differentiation among the people that contribute. And as I stated earlier, off-chip coherency from different vendors we believe is going to be somewhat difficult. It's a layered approach. What I mean by it, because it is packetized, the core architecture defines operations, the protocols, and the physical layers with speeds from 10 to 100 gigabits per second, and in the terabytes in the future, or terabits in the future. And again, we talked about the different signaling rates that we believe we're having at the physical. We're starting out at 16 in our demonstrations that we have, basically relying on the PCIe transports, and going all the way up to 112, which was just talked about using a PAM4 encoding. There's, I just threw a bunch of terms up here kind of as a collage. Not to dive into any of these in particular, but I would encourage the website is open. The specification, I can get you some more detail on it, and I can sure point you to the people that can get you access to it. The security supports multiple hardware enforced isolation mechanisms. Isolation migrate probability of error or failure ripple effects. What that simply says is lots of times we have a memory error, and we'll have the whole server comes down because of a single memory error. One of the goals of GenZ is to isolate those errors and make sure that the whole server doesn't go down. All violations are immediately visible to the detecting component and peer when applicable. All violations immediately reported to management, so there is a management layer that takes care of this. Isolation does not equal security, so which is obvious, I guess. Architecture supports authenticated communications. Packets contain a hash-based message authentication code, anti-replay tag. Keys are protected with AES-256. Multiple secure hash technology is supported. Communication components validate the security field so the people receiving those components verify those. For authorized peer components, untampered packets, unreplayed packets. All violations immediately visible to detecting components and peer when applicable. All violations are immediately reported upstream. So, I want to give you a couple visions of what a server might look like in the year 2020. I know we kind of left that open for in the previous discussion of when GenZ would be around. We have a lot of gates to go through before we get to that point, but we're kind of shooting for products in that time frame. But we see the legacy will still have some PCIe slots. We still have the DRAM going off to the sides of the processor. We're not getting rid of that. But we do want to expand and have larger memory pools out of GenZ links. So if we think about what that physically might look like, the processors, we've worked on several different high-capacity memory modules that would fit inside the chassis, which is not conducive to hard user swapping. We've also had the concept of memory drawers or memory, just like you have a disk drive you plug into the front, how would you take memories and plug in? Persistent memories. And then if you take it to the rack scale where you might have different types of things, you know, FPGA-based accelerators, memory accelerators, you know. So we talked a little bit about GenZ as an organization. I know the previous conversation, he started out with it. I'm going to end up with it. We're a transparent organization. It was formed as a nonprofit. We have wide availability standard. Will be published and available for free. And it's a user choice. And we're also equality, GenC does not favor one implementer over another. As stated earlier, the specification was actually originally written by HPE. It's been modified since by all the contributing members, but the original work, we have to give our nod to HPE on that. Summary, it's a scalable, universal interface for interconnect and protocol. It optimizes memory semantics. It breaks what I talked about, the processor and memory interlock during the development cycle and during release cycle. It enables a hybrid of both data-centric computing and hybrid computing. Opportunities to simplify, we hope, the software overhead and complexity for big problems rather than dragging it in off of a disk, blowing it into memory and operating on it. Heck, just leave it in memory and let the next processor come over and deal with it. Let the next processor come over. Why move it? Keep the patient on the table. So that's kind of the analog I always had on that. Scales across multiple solution sets. Here's our current 31 members, which I'm sure some of you remember. Any questions? I got 1 or 2 minutes. I'll take a question. Sure. I might not be able to answer them, so.
I mean, this looks like a great hardware-centric approach to solve the multi-memory problem. So I have a couple of questions.
Yeah.
One is, if the disaggregation of processor memory is the goal, probably this might solve. But then, like, we have different kinds of memory. Some are high latency, low latency, high bandwidth, low bandwidth. Looks like it's going to be hierarchical. It's not going to be one-to-one, point-to-point. So which means, like, there's a significant software part of it. And that looks like kind of missing here. Is there any plans on the software ecosystem, and what's the approach that's been taken to solve the multi-memory models?
My peers up at EMC have been working at some ideas along that line. I think you're hitting it right on the head. We do need more work in the software. I know from GENZ, we've been courting several of the software OS teams to get more involved in it. But you're right, currently you just have a pool of memory. The processor just sees all memory, and it's all the same speed. It's one hunk of memory. In the future server environment we see, there's going to be different kinds of memory for different purposes. The way to segregate it, the way to allow applications to take advantage of it, I think all that is very important, and it's area that needs to be addressed as an industry.
Right. And
so I agree.
Is the expectation that it will be solved by 2020 to have the pyramid of memory to be handled in parallel?
What?
Is the target to solve this by 2020?
I hope if we're going to have product by 2020, it has to be solved within this year.
Thanks.
Yes, and just like InfiniBand, I think it was mentioned earlier. I was around at the Moscone Center in 1999, so InfiniBand was a collision of multiple technologies. So I think maybe, hopefully, this will be a collision of multiple technologies.
Just to add one more item,
yes.
Seeing the pyramid, at least my personal feeling is like coherence is not the solution for everything. Coherence works for the ones which are on the top of the pyramid, but I think probably we may need a dual approach, partly coherent and partly where there is external control by software or application specific. But again, like, I don't think we have a solution as of now or today, something for the software guys to solve.
No.
Yeah, thanks.
Any other questions? Well, thank you. I appreciate it.